5.3 Definite Integrals Video 2. I want to go ahead and we have a theorem talking about integrable functions. If a function is continuous from a closed and bounded interval, and so it's bounded on this interval, we have a finite number of discontinuities, then the function is integrable. So for this example here, I have this given function and I'm going from 0 to c. And if I use different, we don't know what the function is, but if we have just areas in blue for each piece, whether it's above or below, so we're completely bounded, so we can go ahead and say, what is the value of this function from 0 to a? Well, from 0 to a, which is here to here, it has an area of 16. And then the next one says, okay, well, what is the area from 0 to b? So from 0 to b, we can see that we're going to have the 16. And then we have to have the area that's from A to B that is below the x-axis. So we're going to say minus 5, which is an area of 11. And then if I want to go ahead and say A to C. So we're going to go from A, B, to C. So we can go ahead and say, well, that area from A to B is below the x-axis, so it's -5 area. And we're going to add it to the B to C area, which is 11. And then we can see that it ends up being an area of 6. We are going to have a couple of these for homework, but it follows that same concept. So then I have reversing limits and identical limits. If we have a given standard form of this integration, it should be from A to B, lower bound to upper bound. But if they're giving us one where the values are switched, B to A, we can say we can reverse our limits, but by taking the negative of the integration. So if we want to make sure the bounds are going from lower to upper, left to right on the number line. And then if we have a second one here that says if it's the bounds are from A to A, it's 0. We went nowhere. We have no area on the graph to calculate under. So that makes sense. It's 0. So I want to go ahead and do an example of number 41. And I'm given the function from 0 to 4, the integration of the function 3x times 4 minus x. That's our height. Dx is the width. Our bounds are from 0 to 4. It's telling us this area is going to equal 32. So we want to go ahead and try to manipulate this as we can with using some of the properties that we just did. We're going to actually use some that's from the next slide too. But for the first one, I see that this f of x is the same and matching, but my bounds are switched. So I'm going to go ahead and say it's the negative of 32 because I'm going to switch the bounds. Now, this b, I have the right bounds, 0 to 4, except my function was manipulated somehow. Somehow it looks like if I was to multiply in a -3, I should get back to the function I had originally here. So it's like they factored out a -3. So that would help with making that match identical. So if this is the case, well, if I pull this -3 out in front, and I'm going to show you that it's called a constant rule, what happens here? Well, the original function was equal to 32, but they went ahead, factored this out. That means I now have to divide by that -3. So my answer really should be a -32 divided by 3 because they factored it out. Okay, so they divided both sides by that. All right, so then this last one I have, or not my last one, the next one, C, that I have, I can see from the original function, the only thing they did is, looks like they multiplied. So here, this is going to equal to 32, but it's now more. It's not less, like b was less than what my original function was. This was they multiplied it by 2. So they have to multiply this by 2. And then checking my bounds, I'm not 0 to 4, I'm 4 to 0, so I want to be able to reverse it and invert it, so it's going to be negative. So I'm going to end up with a negative 64 for my area. The last one, our bound is from 0 to 8 of the function, and we don't know at this point what to do with that. That's not what was part of our given information, so currently we're going to say that it's not possible. We will be able to figure that out eventually. If it makes it easier to calculate areas at certain points, there is a rule that says, well, we can split these functions or the areas apart and just add them up. But notice our bounds on this picture. This integral is from a to b. But if I pick some point c in between, I now go from a to c and then c to b, so that I cover the entire interval I really want to evaluate. But I can split those apart, and I can manipulate things with that. So for example, I have here from 1 to 4 as our bounds, a function f of x dx is equal to 8. And I have another integral that's from 1 to 6 of f of x dx is equal to 5. So we want to evaluate from 1 to 4, but we're going to go ahead and multiply the answer by negative 3. And we kind of already did that in the previous one too, the previous problems. So all we're doing is we're multiplying it by the resulted area by some constant. We're going to call it c, or negative 3 in this case. So negative 24 should be my area. And then if I go ahead and I see 4 to 6, I have a number of things going on here. So my bounds are not correct, numerical order. And then I have 12 times this function. And then 4 to 6. I don't even have that in my given information. I have 1 to 4 and 1 to 6. But if I want to rewrite this and it's correct, we'll do negative from 4 to 6. That constant 12, actually, the more I think about that, that's just, I can factor that out. And now I have something a little bit closer to what we were originally given, but I have this 4 to 6. Well, if I can add two areas and I don't have a given number, so something that's not given yet, maybe I could subtract the two areas. So from here, I'm going to have negative 12. And then I'm going to say, I'm going to go from 1 to 6, and I'm going to subtract the 4 to 6. Whoops, I'm sorry, the 1 to 4. I'm sorry, let's do this again. From the 1 to 4, f of x dx. And then I can see that that should then leave me with 4 to 6. So if I go ahead and calculate it that way, my answer should be plugging in. I have negative 12, and the first function was 5, 1 to 6, minus, and then the function 1 to 4 had a value of 8. So I have now negative 12 times negative 3, or 36 is my answer. All right, another example, which I kind of ran into a little bit here. I'm given everything in the black. I have a f of x function from 0 to 3 is equal to 2. F of x function that's from 3 to 6 is equal to negative 5. And then I have from 3 to 6 the g of x function, so two different functions. And then I have here that I want to evaluate from 6 to 3, f of x plus 2 times g of x. So we can do the same manipulations that we've been doing. If I want to reverse the bounds, I have this. And then from here, I'm going to go ahead and substitute in some numbers. From 3 to 6, I should have that f of x from 3 to 6 is -5 plus, and then that 2 times the g of x, well, that 2 is going to multiply the area. I'm going to pull it out as a constant, 3 to 6. So it really should be 2 times that area of the integral from 3 to 6 of g of x of x. g of x dx, I'm sorry. Let's go ahead and simplify what's inside the brackets and not forgetting that we have a negative on the outside. My answer then should be an area of 3. My last slide here is properties of definite integrals that we have in our textbook. And I want to go ahead and it's everything that we've already walked through. The key thing is that you can see number 6 says the function absolute value of f is integrable on the interval a to b is the sum of the areas of the regions bounded by the graph and the x-axis. So I wanted to bring that in and talk about that. If we want to evaluate the absolute area, that's going to give us a total area and not a net area. Because if we're given a function like this and we want to evaluate, say, from here to here, you notice I'm going to have this area here, this area below, and this area above. But that would give me the net area. The total area is if I do the absolute value. So this would then change this function. I'm sorry, hold on. So now it's going to calculate as positive this area, and this area as positive, and it's going to give me a total area. So yes, part of it that was below is now above because it's absolute value, it's only positive values. So we will get a total area for that, and that's what it's saying for number 6.